So today I will talk. I will give this talk. I titled it "Acting Dumb," which includes some of the names of the papers that I'm going to present here. But like, I also try to give it an overall meaning, which is indeed what can we learn from attackers. So. I mean, this is redundant, but yeah, I'm a PhD student in brain-mind computer science, which is a really weird way to spell cybersecurity, but that's what it is. Also, yeah, I'm in the Spritz group. Spritz is an alcoholic beverage, so I was kind of bummed to change the name, but that's okay. And yeah, my research interests are actually everything is involving AI. My PhD topic should be at least on automotive security, but I'm specifically focusing on machine learning and deep learning applications. And finally, I also have cyber threat intelligence as an interest on which we did some works. First, I want to give a brief introduction on what we're going to talk. And then we are going to talk about the two main topics, which are adversarial attacks, cyber threat intelligence. And then at the end, we will have some conclusion to kind of line out what they have in common. So a little disclaimer, this talk is about AI and its application on security and privacy. So nothing new here, but still we try to tackle these topics in a different perspective. Which is alternatively the perspective of an attacker and the perspective of the defenders. So why the title? So AT is like the English name for AGIR, which is AGIR in Italian, which is under the acronym for one of my papers, and dumb is actually also an acronym for the framework that we will talk about. And so first, I want to talk about the accessibility of AI. So in Padua, I'm a teaching assistant for an ethical hacking course. We give students some laboratories to do. So I have been a student too. We all have been a student. So now that we have ChatGPT, let's say what happens if I ask him to generate a reverse shell code. But of course, ChatGPT says no, because this is illegal, you cannot do this. But once you say that this is for an ethical hacking class, everything is okay, right? So the main point of this is that we are sort of shifting from the perspective of the hacker, from this crazy guy tapping on the keyboard and somehow he's skilled in maths, because that's what stereotypical figure of the hacker is, to something that is just laid back and can have AI do everything for him. And also, I was very impressed by the fact that these, of course, are AI generated, and it nailed the writings, which is an improvement over last year. So this kind of accessibility, though, goes both ways. So if attackers can perform attacks using AI, as defenders, we can also use AI to defend ourselves, right? So you have endless possibilities, yes, as long as you have the data. Think, for example, of anomaly detection, intrusion detection systems. As long as you have the data, it's pretty easy to do a model that can also overfit. You don't really need to like engineer that much what is going under the hood, but they show that it works. But there is a problem, right? So AI is also vulnerable. And it's always this panda/gibbon. For those who does not know what this is the like most popular example of adversarial attacks. And these adversarial attacks are sort of what are threatening AI models right now. And that's my segue to the first topic that I want to talk about, which are adversarial attacks. So here I will give you a brief introduction what they are. So suppose that you have binary classification tasks. So you want to recognize cats and dogs, so in a computer vision manner. You have a clean input sample, you train your model. Supposing that you do everything right, what you have is that your model says that this is a cat, and that's okay. Adversarial samples are a sort of these are these inputs that are modified in such a way that include also some computations of the gradient in order to generate an image which is somehow the same, somehow different, which in this case, by the same model, is classified as doc. So this is an exaggeration of the effects of adversarial attack. There is a parameter which is called epsilon that handles how much you modify the sample, because of course, once you have the clean one, you will see the adversarial one and can say, okay, there's something wrong here. But the model does not see that. So when we were working on this, we were asking ourselves about one property of these attacks that is transferability. So what is transferability? Suppose that we have in the same task as before. So we have the sample, we feed the model, and from the gradient of this model, we can generate this adversarial sample. This sample, when I use it as input to the target model, which is the one from which we generated the sample, of course, if we do everything right, will give us that it's a doc. But what happens if I want to attack another model? And this is what we talk about when we talk about transferability. So it's the property of adversarial attacks to transfer among other models. And this was something that we really noticed in the literature, because these attacks are amazing. These are really amazing. The only problem is that most of them require some sort of access to the gradient, which is somehow not really realistic, because if I want to attack the computer vision model of a Tesla to cause an incident, I don't really have that. So how can I do that? And from a defender perspective, how can I evaluate if my system is robust enough to defend against these attacks? So that's why we created this dumb testbed. So we have a surrogate model and a victim model. But what happens if we do not know the model? What happens if we do not know the dataset? What happens when we are in a sort of black box scenario? So in this case, we selected 3 different metrics to perform our analysis on. So the first one is the dataset source, which is the DU dimension. So this means, for example, if I have these models, I have a computer vision model, I am using the dataset that has been crawled from Google or that has been crawled from Bing. This is an example. Then, of course, the model architecture, because that's probably the biggest impact that an adversarial attack will have. So what kind of model are we using? What kind of parameters are we using to train this model? And finally, the balance level. So the balance level comes from an insight on specific tasks, especially in cybersecurity. Think about hate speech detection. So when you want to, maybe you are a social media company, you want to detect hate speech, so you are collecting a data set from your platform. However, like if we suppose that people are nice, we can see that maybe we have an unbalanced distribution towards the positive label, and only a fraction is negative speech. So what happens if like this distribution of the labels is different? So what if it's 50-50 or what if it's 20-80? So from this, we came up with this dumb testbed. And so we have these 3 dimensions, and of course we consider all the possible combination. This means going from a black box scenario in which an attacker does not know anything, distribution, dataset, and model, to a white box scenario, which is somehow the most common in literature, in which the attacker knows everything. And of course, in the middle, we have 6 different gray box scenarios. So we can have a scenario in which we have the model, but we do not have the dataset source and the balancing. And we can have a scenario in which maybe we do not have the model, but we have everything else. So this work has been already published. You can find the paper online. So we gave some insights for each of these scenarios, so sort of real-world example. This example can be, let's say that we want to attack the hate speech task. We want to perform an adversarial attack on that. So maybe we are on Twitter or X, and we suppose that we have access on all the data, and we have access to the distribution because that's the dataset from which it will be trained. So we have that, but we do not really know the dataset that maybe X is employing to do this kind of task. And so this is the kind of transferability that we are trying to test. And of course, we are testing every possible combinations of this. So in our study, we employed binary classification in a computer vision task. So what we did was to extract 3 different tasks, which are indeed cat and dog, bike and motorbike, and man and woman. So it's everything has 2 labels. We're not considering them as positive or negative, as in a classic binary classification task, but we are just sort of giving the baseline to go towards multi-classification after, which we did not do for the moment for the reason that we will see soon, which is that we have too many experiments to perform. Because what happens here, we also have to define which are concretely our dimensions. So for the dataset source, we identified 2 different sources, Google and Bing. So we collected the datasets with the classic validation. So we manually validated them, or we preprocessed them to have them in the same format. And also we removed duplicates. We selected 3 models, which are ASNet, AlexNet, and VGG. And we did this just because they are sort of the state of the art and they are easily accessible, especially through Torch libraries. And finally, we have 4 balance levels for the dataset. So we start from a balanced distributions of the labels, and we go to a strong imbalance between the labels, with 2 other medium settings in the middle. So this means that we have, just for baseline, 24 different models for each task. Why? Because let's say that we are working with cats and dogs. So we want to train 3 models, which are AlexNet, ResNet, and VGG. But each of these models must be trained on a different dataset. So we have Google and Bing. However, each of these datasets needs to be processed in order to have the kind of imbalancing that we want. So 50-50, 60-40, and so on. So for each model, we have 24 models. And this is just for evaluation. This is evaluation that is this one. So we did the classic thing. So 70% in training, 10% in validation, and 20% in test. And also here we report the results for F1 score because we wanted to be balanced somehow between each score. And immediately what we can see here is that we have some pretty good results, let's say. What we can see immediately is that there are some tasks that are more complex than others. This means that, for example, men and women, this is for some reason the most difficult to train on, and AGIR are the models, so let's not VGG. So immediately we have sort of insights on the fact that bikes and motorbikes might be the easiest task, and men and women might be the most complex task. So here we did not really focus on optimizing these kind of models. We used I think that we did some, of course it was fine-tuned, and that we somehow tuned the hyperparameters to be consistent among these models, but we did not really focus on making them as good as possible. That's because this fact can actually be a good insights that we will see later. So now that we have the baseline, we can start attacking these models. So also here, we divided attacks in mathematical and non-mathematical attacks. So these are sort of weird like words that we put together in order to distinguish different things. So mathematical attacks are the real adversarial attacks that you see in literature. So it can be your bread and butter as FGSM, or it can be sort of more complex stuff like deep fool or a square attack. In each of these attacks, there is the computation of the gradient in some way to generate the attack. Then we wanted also to study non-mathematical attacks, you call them, but it's just applying a filter. So it's just an image transformation. So what happens if we just blur the photo? What happens if we add noise or we do weird stuff with the coloring? And these, of course, do not involve any computation. This means that these samples are generated directly from the model. So you do not need any gradient. You do not need to have them trained on some weird stuff. So we wanted, the point of this is, if we do not know anything, maybe just changing the colors is better. Can that be? And so we started testing. And now you will see why it becomes really complex to do this kind of stuff. So this is the overall pipeline of our experiment. So first we select a task. This is like bikes and motorbikes, cats and dogs. Then we select the attack. And this is just for the mathematical attacks. We select the attack. And then we select a source model and a target model. So the source model will be the model on which the gradient computation will be performed in order to generate the adversarial sample. The target model instead is just the one that we want to use to evaluate our attack success rate. So, of course, we have 24 source models, 24 target models. We have 7 attacks, 3 different tasks. Then we also have the non-mathematical attacks. This resulted in around 13,000 experiments, which I was giving the spoiler before, was nice because we did it during before Christmas break. So the GPUs in our office were hitting the office enough to not open anything. So it was very nice, but not so nice when you realize that there is a bug that you implemented 2 weeks before and you got the result on 2 weeks after. But that's another issue. And so we go to the results. So also, like, it was funny because when writing the paper, it becomes difficult, right, to show these kind of results. So we kind of crafted out this weird thing that we call JoJo plots. I don't know. And has anyone of you see JoJo's Bizarre Adventures? Whatever. These are sort of weird stuff that I will explain now. So here you have your scenarios, right? So from C1, which was the white box scenario, you go to C8, which was the black box scenario, and everything inside is like sort of gray box. So each of the histograms here represent an attack, and then inside here you have the mean of the attack success rate of that specific attack. So immediately what we can see here is that some attacks are working better than others. So like, for example, TI FGSM works better than the standard FGSM in most cases. But another thing that we can see here is that the models that were performing not bad, but worse before, are also the ones that are most susceptible to our attacks. This is because we obtained like 0.99 everywhere with bike and motorbike. Instead, with men and women, it was kind of 0.85, something like that. And indeed, what we can see is that TI-FGSM is high, is very high, especially in those cases that we will see before. But we reach attack success rates of up to 0.89, stuff like that, which is enough to disrupt the whole functionality of the system. So also in this case, let's focus just for the sake of this takeaway on one attack, which is the TI-FGSM, which is the most noticeable one on the men and women task. And I want to like point out cases C1, 2, 5, and 6, which are these ones. And these ones are the cases in which the model is the same. So I don't remember exactly, but here, for example, the model is the same, but the other 2 dimensions were unknown. So what we can see here is that these are actually the best, the scenarios in which the attack performs best. What this means is that the model is actually the most influential thing that you can have when you want to perform an adversarial attack. This is not entirely new. There is a very nice paper called Real Attackers Do Not Compute Gradients, in which they kind of give a lot of takeaways like that. It's very interesting. If you're interested in this kind of scenario, I highly suggest it to read it. But what we can see this is that we somehow confirmed what we were doubting before. So that indeed the attacks in the literature are very effective, but having access to the model is imperative to make them perform better. So at this point, we also asked, okay, so let's see what are the non-mathematical attacks that outperforms the mathematical attacks. So what are the cases in which modifying just a picture can be better rather than computing an adversarial attack and maybe using a surrogate model or stuff like that? And indeed, what we can see here is that the other 4 scenarios, so the scenarios in which the attacker model was different from the victim model, are the cases in which doing a salt and pepper image modification on the image might be better than just performing an adversarial attack. So simple obfuscation, solid. Of course, easier to detect if you do something before, but are still solid black box techniques. Then we started to analyze other stuff in the other dimensions that we had. So here, for example, we report the attack success rate for the minority and majority classes, and these, of course, are meaned across, are averaged across all the other dimensions. So immediately, what we can see is that the mismatch between the class distribution might penalize transferability because, for example, here we can see that we have higher attack success rates in specific areas rather than others. But most importantly, that attacking the minority class is somehow easier compared to the majority one. So this is something that also we thought about before. And the hypothesis was that when you try, in the feature space, when you try to move one sample from one cluster to the other, if that specific space is smaller, it might be easier to just jump on the other part. And this is indeed something that we saw also empirically. And finally, we wanted to analyze the effect of the dataset, the source of the dataset. So here we put the just the 2080 balance level because we wanted to somehow show that these results matter. And here we put 2 different tasks. And when we say target dataset, so this orange line means that the attack was generated on a model that was trained on, for example, Bing, and then was targeted on Google. So what we see here is that in cats and dogs, which again was one of the tasks that was performing okay, there isn't that much of a difference. Instead, the attack success rate has a slight increase when we consider tasks that were not really good, as the men and women, because this is a probability density function, right? So here we can see that attack success rates that we obtain are slightly higher while attacking Google trained on Bing. So we just did this study. We developed this framework, which is available for everyone on GitHub. We measured some new aspects of transferability. There were other papers that indeed were studying other aspects, but did not really focus on those kind of attacks and parameters. Also, by being open source, we think that this is somehow a way to evaluate the resilience of your defenses, as long as, of course, you have the time to train all this stuff and the computational power, of course. It is nice because once you want to design a system, of course you design a system model, of course you design a threat model, so you know what are the possible information that an attacker might have. So you may know that, for example, you may be susceptible to the C5 scenario or something like that. So by looking at this, by testing on this, you can indeed see if there is something that you need to be aware about. And also, like, of course, we have some future works, and indeed, like, right now we are trying to test it on poisoning attacks, because this one was on evasions. So this is something that we are actively doing right now. Hopefully we will obtain good results and we will publish them soon. But yeah, so this was basically what we did on adversarial attacks. And I want to now somehow change topic and go to the other works that we did in our group on cyber threat intelligence. Because, of course, like right now we are talking about attacks towards AI, which is something that maybe, I don't know, 5 to 10 years ago would have seemed completely crazy. And indeed, like the types of attacks that have been occurring during the years have been constantly evolving. And while, for example, the use of AI in this kind of scenarios might be something that is maybe not seen as a threat as much, especially by companies right now, other stuff is. So for sure, after 2017 and all the attacks that happened, companies are beginning to take ransomware seriously. At least we hope. But I mean, especially like bigger companies needs to be aware of attacks that might come from advanced persistent threats. These are very sophisticated attacks, very sophisticated groups that have like a full pipeline to perform these kind of attacks, from the preparation to exfiltration of data and cleanup. So how did they manage to defend until now? And the answer is cyber threat intelligence. So cyber threat intelligence can be defined as like collection, analysis, and hopefully dissemination of this of data on this kind of attacks. The idea here is that once you know how an attacker operates, you can also sort of do your defenses accordingly. And I mean, it's a big business right now, but it also allows you to sort of avoid spending a lot of money on these attacks. And indeed, one example is the denial of service attack of the Reaper IoT botnet. It was a denial of service, but some companies were disseminating knowledge on these kind of vulnerabilities before. So some of them were able to identify some vulnerabilities that were used in the CNC infrastructure, and they were somehow mitigating this attack. But yeah, this is all useless if you do it, not useless, but like if you do it internally, it benefits only you. So a big part of cyber threat intelligence is sharing this kind of data. But first, of course, you have to collect it. So what happens usually is that an attack occurs. There are some analysts that study what happened, indeed, in order to extract some intelligence. And this is still at a high level. So you know what happened, you know what are the tools that have been used for this kind of attack. And then you have to share it, either publicly or internally, to the guys that have to do something about this, right? How do you share it, though? So you have basically two options. The first is natural language reports, which is just, I don't know, English. You say attack X occurred using tool Y. Or you can use structured information. So you have the most common one that that's been used until now is STIX, which is a sort of language to encode this kind of information. And then there is TAXI, which is a sort of exchange protocol in order to share it. So these methods have all their pros and cons. So for example, with natural language, can be understood by everyone. But in structured data, you have better machine readability, right? So the problem becomes, how can we go from one side to the other? So the idea here is that you start from a natural language report. This is just an example, and you want to go to a sticks graph. So you want to have entities, you want to have relationships, and this must be encoded in the sticks format. So how can you do that? We work on that. There have been actually many works on that. But what we noticed is that they were somehow focusing on specific types of entities. This means that there have been several works with very good performance that focuses on a specific subset of threat actors or a specific subsets of sticks entities or relationships. So what we saw is that there was something missing, which is a tool to include everything. And that's why we developed SticksNet. So SticksNet is a tool that we developed to do exactly that. And in doing that, we are including all entities, all sticks entities, and all sticks relationships. And in this way, you can have a graph, which is then converted in a report, which is then converted to a full graph. We did this work with the collaboration of an Italian company that allowed us access to a knowledge base that already contained a lot of information and a lot of intelligence. So we actually leveraged this, both before and after. So before, what we did is use it for the extraction of known entities. And after, we use that to sort of store the new entities that are detected in order to be more easily recognized in subsequent execution of the tool. And finally, we did this all in a pipeline approach. This allows us to have single modules, which is somehow important for companies because maybe they paid a lot of money for a module, so they do not want to swap that out. And also, it allows to have different results that you can integrate together. And of course, we manage also that. So let's go briefly through the pipeline. So we start from a PDF report. Of course, we extract text and we sort of process it because, especially from PDFs, something weird happens. Like you have some characters that may not be recognized. So we have to take care of that. And then we can go to the entity extraction module, which is composed of 4 different submodules, each specialized in different types of entities. We merge the results, of course. And then we go to the relation extraction module, which relies on the entities that have been collected before. Finally, we have our output. Here we put JSON, but it's just a sticks, it's sticks compatible, but it's a JSON. So let's start. We will go in on each submodule one by one. So starting with IOC Finder, which is somehow the easiest one because we are just collecting indicators of compromise. These can be like IP addresses or CV names or stuff like that. So after extracting the text is a simple matter of regex rules because they all have the same structure. So it becomes easy to extract them. And of course, all of them are supported by sticks. There is an object, a sticks object, which are the indicators. And then you can specify what type of indicator is this. And then we go to the knowledge-based entity extraction. So as I was telling you before, the idea is that we have this kind of knowledge. Why not using them, right? So what we have is that after we process the report, we divide each sentence. And from there, we use our database that has a lot of entities inside. And this includes names, aliases, IDs, properties, and a lot of stuff. So we have the names, right? So like if I talk about APT1, I read APT1 in the sentence, why not extract it, right? That seems so easy, but it's you don't need to handle it because it's a stupid approach that is going smoothly only if you take account of errors. So, for example, the word "us" can be a location if it's the US, or can be a pronoun, right? So I can go on all my reports and every "us" will be a location entity, right? So what we do is that we use NLP, which is natural language processing, to perform part of speech on each sentence. This means that if I recognize the word US as a noun or proper noun, because it's all in caps, then it would be a location. If indeed it's a pronoun, I don't recognize it as a location. And after that, you just have a list of sentences and the entities that are contained inside them. However, of course, some reports are published on new attacks, on new actors. So we need to take care of this. And to do this, we employ this, we call it novel entities extraction. They are novel just because they were not in the knowledge base before. So what we do here is that we already have the NLP processing that we did before. Now, we are not really interested on the part of speech, but we are interested in the dependency between these type of tokens. So what we notice now is that each of these entity types present a sort of pattern in these dependencies that we can actually detect. So once we detect this, we can see that a new entity was there, and then we can select it and possibly add it in the knowledge base. And finally, another big challenge was the TTPs, which are tactics, techniques, and procedures. So until now, we have extracted everything that has a noun. So for example, the WannaCry ransomware. WannaCry is something that you want to extract. Here instead, you want to extract something that is slightly more abstract, because you are sort of defining what are the tactics that an attacker has employed to perform the attack. So this is a sort of implicit in the text, but not explicit, like saying, okay, we use the T1518 in the Mitra attack framework. So what we did was to improve on an open source project, which is called, I don't know, CAT, RCATT, I don't know. But you can find it in the paper. And we improved on that by retraining it fully with the original dataset, the new data from the Mitra attack framework, and other external sources. So we obtained slightly better results. And this tool is a sort of a classifier. So it takes full reports or sentences, encodes them, and then classifies them according to the different tactics and techniques also allowed by the Mitra attack framework. So now what we have is a list of sentences and the entities that are inside them. What we do now is to extract relationships among them, right? Because you have them, we know that each couple of entities will have a relationship between them if they are at least in the same sentences. So this is what we do. And also in this case, we have two different submodules. In the first one, we do something also here. Not really stupid, but convenient. So what we have is that we already have the NLP processing of the sentences. So we also decide to use it again. Because now you can generate graphs of these sentences in which each node is a token. You are really not interested in the edges. In this case, they might be the dependency that they have with one another, but we are just interested in the fact that they are somehow connected. And from there, you identify the entities. And for each couple of entity, we just computed the shortest path. So what happens is that you have stuff that is pretty much usable. So APT29 is a threat actor, 7zip is a tool. We have the word use, we can lematize it. So this is a threat actor uses tool. And that's a sticks relationship. And that's okay. It becomes somehow harder when we have multiple verbs, and maybe they are very far away from each other. So what we do here is to extract the verbs, and lemmatize it, of course. So lemmatization is just, instead of having it as used, it will be use, just with rules. And then what we do is that we see what are the types of the entities that we are considering right now. We look in the list of 6 relationships, what are the relationships that can occur among these 2 types of entities. And we compare the verbs in their lemmatized form with the ones in the sticks protocol. So now we also use a confidence score to have this, and we employ a threshold. So if the confidence of a verb between these two is too low, we do not consider them. If instead is over a certain threshold, we consider them as a relationship. And as I was saying, this is fine once you have like entities that are close together. It becomes somehow harder when you have entities that are far from one another or are in different sentences. So we have another submodule for that. This is the deep learning-based relation extraction. So what we use here is a sort of encoding that we do with a sentence BERT. It's like a modification of the BERT protocol. And then we also use another time a similarity value in order to also employ the threshold that we previously defined. So what happens here is that we have a sentence. We perform the embedding. We compute the embedding. We have our list of relationships. We, of course, like trim it down with the relationships that only contain those types of entities. We compute the embeddings. And from there, we compute a similarity, the similarity between them. And if it's over a certain threshold, it's a match. And of course, we normalize these thresholds that we employ and also the similarities that we employ, because like you can merge these relationships together from the 2 submodules by looking at the confidence scores. So these are the results. We divide them in entity and relationships, and we also divide them in 2 different scenarios. So in the first one, we have what we call an interactive knowledge base, but basically what happens is that after a certain amount of reports are collected, an analyst manually validates the new entities that have been extracted. So we do this because we received some feedback from this. Indeed, we noticed that in the long run, if you keep adding stuff in the knowledge base which is not validated, your performance will drop. So instead, we are still somehow automating this process, but instead of fully extracting each entity one by one, you just have to see, okay, this is a new malware. That's correct. Yes. Okay. That's it. And what we see is that by doing this, after each batch of reports, we have an increase in the F1 score and also precision and recall. We did not use accuracy because there are multiple levels. So the other part indeed is the static knowledge base. So the novel entity extraction module is working, but it's not adding anything to the knowledge base. And then we go to relation extraction. So here the results are slightly lower, but we noticed also that there is a problem in the fact that entity extraction and relation extraction are in a pipeline. So each error in the entity extraction part will be carried over to the relation extraction, and it will be multiplied by the times in which another entity is present in a sentence. So what we noticed is that if we remove these instances, the precision gets a little bit higher, but the recall slightly goes lower. So the F1 score is comparatively the same. But the takeaway from this is that if we want to employ a pipeline approach on this, the first module must be as good as possible. Otherwise, you will encounter these kind of problems. And this is basically what we did. We presented this work last year. And so in the meantime, we were wondering what if we want to do the opposite. So for everyone here that was in Sorrento last month, this will be the part in which you can sleep a little bit. Because we are going to talk about AGIR, which is a tool that basically does the opposite. So instead of going from natural language to sticks, you want to go from sticks to natural language. And you might be wondering, why should you do that? You did work before just to circumvent this problem. The fact here is that generating a report is not that easy. And especially if you're a company that specializes in cyber threat intelligence, this might be your revenue, a part of your revenue. So after you have this amount of data, generating a report starting from sticks language is not so easy, but can be done automatically, and that's what we did. We employed multiple templates, and we allowed, of course, every type of sticks, entities, and relationships. Of course, we still had the help of the company, so we had this knowledge base, which we use for integrating entities together. So like merging stuff together. So like each time we see an entity, it does not create another entity, but only the different properties will be merged together. And we will also use it for entity lookups, of course. In this case, pipeline approach in order to support for additional templates in the future, and also like to have an easier integration between the modules. So before going to the pipeline, this is our system model. So we suppose that we have a source of different sources of intelligence, actually, that are somehow converted to sticks and are present in our knowledge base. From there, we have our system that just takes the input of the user, just says, okay, I want a report on these types of intelligence, and from there we generate a report. So this is our pipeline. Our inputs are two things: the sticks graph, so the point on which we start, so which is the intelligence that we want to include in our report, and the report type. We include 4 different templates that we will show you in a while. Then we have 2 main modules. The first one is a template-based module. So what happens is that based on the type of template that you want to generate, you filter some of the entities that are present in your inputs, and then there is just an entity lookup submodules to extract the intelligence from the knowledge base. From here, you generate. It's a report, but it's not really finished. We call it first stage AGIR report. I forgot. AGIR stands for automatic generation of intelligence reports, while Stuxnet was just a wordplay with Stuxnet. Then we have the neural-based module, which is actually, its purpose is to just keep the information as it is, but like make it more fluent. So of course, we have, like we communicate through APIs with our large language models. Guess what it is? And finally, we have our final report, which is the final product of our tool. So as I was saying, 4 different types of report. So the first is overview, which just uses the intelligence that you have in input. Then we have subject, in which you focuses just on the node with most connections. So it might be, for example, a report that treats a particular threat actor or a particular incident. Then we have the timeline, because in our knowledge base we also include the times on which the entities are collected. And finally, vulnerability, in which we are treating specific CVEs. So, as I was saying, there are some lookups from the knowledge base. These are handled with API calls, and there is, of course, IDs to merge, as I was saying before, like intelligence together. What happens under the hood is just basically we are filling a dictionary. So we have these 6 keys. So, for example, for each entity we extract that is present in the input, we extract the IOCs that are related to it, the TTPs that are related to it, and so on. And yeah, so we have first step report. It's okay, but it's a little bit robotic. the intelligence is there, but it's difficult to read. So with GPT APIs, we just tell him to keep everything the same, but make it more fluent. And now we have a report which is more readable. But in this case, we were somehow worried about the fact that this process actually messes up things because maybe we are losing information and maybe we have hallucination. So the first kind of evaluation that we did was a quantitative one. So what we wanted to see is that if this module actually does something bad. The answer is no. Precision is 1. This means that there is no hallucination going on. Recall 0.993. This means that a really small fraction of the intelligence is lost in the way. We try to improve on that to have 111, of course, but regardless of the type of prompts that we gave to GPT, somehow there were a couple of instances in which intelligence was not ported after. But of course, what we are more interested in is the fact that these reports are actually usable by humans, because otherwise you can just use sticks data. So we had a qualitative evaluation, which is also split in two. So in the first one, we wanted to have a sort of objective metric to measure how fluent our text was. So we used SLOR, syntactic log-odds ratio. Apparently it's something that is used in literature. So, okay, this metric is technically unbounded. So, and depends on many stuff. So it depends on the type of data that you have in your report, of text that you have in your report, and on the language model that you are using to compute this metric. So instead of the absolute values, we are interested in the relative one. And we are interested in the relative one also with the state of the art. And this is because the only other work that treated this was Narrator, because it was something that was actually available for everyone this summer when we did this work. Now it's not. So, okay. But what we saw is that the results of Narrator and our first step AGIR are somehow comparable, and this is because also Narrator employs a template-based techniques to create the report. What we saw instead is that we have an objective increase in fluency after the usage of a large language model, which also did not impact significantly our quantitative results. However, we were also interested in seeing how these reports can actually improve the workflow of real analysts. So what we did was to do a user study. We contacted 38 analysts from the company that we work with. These are experienced guys that do, among all the other things, also collect intelligence and write the reports. And we used a Likert scale on 3 different metrics. So fluency, correctness, and utility. And this is one of the most important things. So whether the text that you use from that you get from AGIR can help you in writing the final report that you might want to sell to another company faster. So of course we started from a baseline, and we gave them some sort of sticks graphs, and we asked them how long will it take to write a report on this, and the average was around 2 hours. And these are the results that we get. So we can see that final AGIR is better overall. But most impressively is the fact that it goes from 2 hours to 74 minutes, which is indeed pretty nice, considering that it can be used as a sort of starting platform to generate your final report. And of course, this was anonymized, so the users did not know which model generated the reports, and yeah. So finally, this also sort of links back to the title of the seminar, so acting dumb. Especially in adversarial attacks, what we saw is that effectively a malicious attacker might be done for a reason. Use an Instagram filter on your image, and maybe it's better than do something complicated as an adversarial attack. So they are done, but in not a bad way. The main thing here is that what we saw is that literature on this matter is a lot, and it's very impressive. But somehow focusing only on white box attack, it's not really optimal if you want to do this in a real world. So the simpler the better for an attacker. And so this raises the question, are these AI systems a risk? Since, I mean, we saw that not having access to the model is a good strategy to defend. So let's do security by obscurity. So from a defense point of view, of course, it's important to have a proper threat model. So you might know what is the knowledge of an attacker, but you might also know what an attacker does not know for sure. So this gives you an idea on what you have to focus most. And indeed, like we think that we the proof of concept that we give with them, because of course this will be different from a full-fledged system that you can use to test the resilience of a more complex system. You can somehow test this, and you can indeed evaluate what is that you have to proactively focus on. And that somehow goes back to the fact that you have to know what you are trying to defend against, right? So by having insights on what you need to defend about, you can indeed create your defenses better. And what we saw is also that AI can help in both the collection and dissemination of this kind of stuff. Of course, then there is the matter of the cell attacks on CTI collection. That's like sort of meta project. So like I was thinking, are we going to like a sort of full automation? We are fully automating with AI attacks. We are fully automating defenses. So this is kind of a weird thing. It reminded me of generative adversarial networks. So there is a generator and discriminator that evolves on both sides. But yeah, I guess that understanding the system first would be the most important thing, and that's what we are trying to go on with the research that we are doing at Space. And that's it. Thank you for the attention, and I'm available for questions.